Hi kids, Smath here, and this video is another video in our bonding series. And with bonding, today we're going to talk sigma bonds, pi bonds, exceptions to the octet rule. There's just a whole potpourri going on. And then we're going to wrap up today with Vsepr structures, including, and we touched on that in our last video, but now we're going to hit them and make sure we cover all of the exceptions and when do we apply those rules. So let's get going. We'll get this done as quick as we can. Let's start out with sigma and pi, which is one of the easiest things when we break it down and define what a sigma and a pi bond are. Sigma bonds are bonds that are within the axis of the molecule. And so if I look at my carbon dioxide here, the axis of the molecule is this direction. Nitrogen, this direction. We'll do some later on that get a little bit uglier. But remember, you can only look at a sigma and a pi in terms of one bond. You're not looking at the whole molecule. So don't be thinking about the axes of a tetrahedron. All you're looking at is the connection here between that carbon and that oxygen, or that carbon and that oxygen. And so a sigma is within the plane, all right, within the axes. Now, the note on these is all first bonds, first connections made are going to be sigma bonds. So sigma holds the world together. It's huge, okay? And all single bonds are sigma bonds. So we don't have pi bonds until we have multiple bonding going on. Okay. Now, here's our asterisk, only sigma bonds count towards geometry and hybridization. So pi bonds don't. And I'll come back as soon as we define that pi bond, and that'll make a little bit more sense. But only sigma bonds contribute when we start saying how many bonds, how many lone pairs. A double bond is only going to count as one bond because only sigma bonds count towards that geometry and hybridization. That's what that means. Now, what's our pi bond? This has nothing to do with 3.1417, whatever it is. These are pi, perpendicular to the axes. So the way that I've ever heard this explained is my axis is going to be in the X. Anything that happens in the Y or in the Z, that's going to be a pi bond. Sigma bonds are going to happen in the X. Pi bonds are going to happen in the Y or the Z. Which one? It doesn't matter. We're not concerned about that. So these are bonds that are perpendicular to the axes, and these will only exist in either double bonds or triple bonds. And so if I look at my carbon dioxide molecule, here's a great question. It's like, how many sigma, how many pi? And the board has been known to do this with huge macromolecules, just to see if you can count. And it's super easy to see that if I go, there's a sigma, there's a sigma, there's a pi, there's a pi. Does it matter which one's sigma and which one's pi? No, it's a double bond. One of them is going to be sigma, one of them is going to be pi. We really can't say. These are electrons, they're moving. So we can't say, well, the one on top is definitely sigma. Nah, it doesn't matter. There's an attachment that's in the axes. And so in this case, there are two pi's and there are two sigmas. That's the only part that really matters, is how many are there. If we look at our nitrogen molecule over here, I've cleaned it up, and I've actually cleaned it up and made it hideous at the same time. So if we do nitrogen, it goes 1, 2, 3, nitrogen, lone pair. There are only two things connected here. There's one sigma, there's two pi's. How do I know which one's which? It really doesn't matter. It's just that we are noting how many attachments there are. And as I say, those are important because we need those when we get to the geometry and the hybridization. So that's sigma and pi. It's as simple as counting. If I have a methane molecule, carbon, hydrogen, 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 I don't care what you put on the ends of those things. This thing has 4 sigma bonds, no loners or no pi's. It's that simple. Don't make sigma and pi harder than it needs to be. Okay. We have other stuff to do that. We have exceptions to the octet. Now, I already told you in the last video that groups 1, 2, and 13, they were exceptions to the octet. They don't make an octet. They're less than an octet. Okay. Now we find out in group 15 has to be period 3 or below. How come? Because remember, to get more than an octet, we got to go beyond S, beyond P, and now we got to start using our d orbitals. And you don't get d orbitals until you get to the 3rd period or lower. So this is going to be phosphorus. Poster child for more than an octet. Phosphorus pentachloride. So first thing, check the electronegativities. It's 0.9, so it's covalent. It's polar. Greater than 0.4, so it's a polar covalent bond. And this one, we'd expect to be kind of polar. They're close, but they're not close enough to be non-polar. Start getting into oxygen, fluorine, oxygen, nitrogen, oxygen, and chlorine. They're polar all the time, unless they're diatomic with themselves. They're almost always going to be polar because those are 3 of the 4 very electronegative elements. Now, fluorine's got a high enough electronegativity, it goes ionic a lot of the time. But in this case, we've got polar. So how do we get things far away? Go North Pole, South Pole, and 3 around the equator. This means that around that phosphorus, there's going to be 10 electrons, and that's okay. That also means there are going to be 5 sigma bonds. No pi's. It's not double bonded. There will be a case later on where we use something like this, and it's going to have some pi's. But right now, that's a group 15 exception, period 3 or below. Move next door to group 16, 3 or below. And now you have sulfur hex iodine. I know you're thinking hexafluoride, but that's not going to work. Okay. Sulfur hex iodine. And now this one's drawn really poorly, and I drew it, which is even worse. Let's go North Pole, South Pole, put an iodine on there. And then around the equator, there's, whoops, these are iodines. There's 4 iodines. And remember, everybody gets their lone pairs. Lone pairs all around. So that sulfur is going to have 12 electrons around it. It's going to have 6 sigma bonds and no pi's. So we have the exceptions that are less than octets. We also have these 2 major exceptions that are greater than octets. Now, we're going to go into our next topic, which is also going to illuminate a few more exceptions for us. But these are the biggies, the less thans in groups 1, 2, and 13, and the greater thans in groups 15 and 16. So let's talk valence shell. Vsepr. I know the way it's written, it should be pronounced Vsepr, but it's Vsepr theory. That's what it's called. And it stands for valence shell electron pair repulsion theory. It's a fancy way of saying that the valence electrons in an atom will strive to minimize their repulsion. Well, how do you minimize repulsion? Get as far away from each other as possible. So if we could get things 180 degrees apart, fantastic. Then that's going to minimize the electron-electron pulling themselves apart, which is what they tend to do. This is going to help us predict the molecular geometry, the shape, about the central atom in a covalent structure. We're not going to do shapes of ionic structures. It's not on the board exam, and there are 42 different shapes. Leave that for when you take solid state chemistry in college. So let's go kind of group by group and look at them as generalizations towards what could happen bonding wise. Instead of saying this always happens in group 1 and group 17, say if I have one bond, no matter what, if there's just one bond, doesn't matter about the lone pairs. One bond is going to connect two things in a linear fashion. I can't make that any easier. Connecting A and B, shortest distance is a straight line. Got to be linear. If we move aside and our central atom is in group 2, this thing Sn is called a steric number. It's the number of bonds and lone pairs. So in this case, my steric number is 2. How come there are 2 bonds and no lone pairs? This is going to be a molecule like MgI. Excuse me, MgI2. Okay, and that's going to form sigma bond, sigma bond. You have 3 things. What's the easiest way to get 3 things as far away from each other? A to B to C. Line them up all linear and make that bond angle 180 degrees. Okay, super simple. There's that definition of steric number. It's the total bonds plus the lone pairs on the central atom. I know there's tons of lone pairs on the iodine, but that doesn't matter to us. We don't care about the iodine. We care about the central atom. All right, the bond angle is the angle between 2 bonds. So it's not the bond angle really between magnesium and iodine. What it is the bond angles between that bond and that bond. That's the difference there. Okay, let's keep going along. Let's move across the transition metals and look at group 13 just a minute. In group 13, I've got aluminum trichloride or aluminum chloride. Okay, trichloride's a common name for it. It has a steric number of 3 because there are 3 bonds and no lone pairs. I draw it out. I got 3 sigma bonds, no pi, 0 pi. This is going to form a shape called a trigonal planar, and it's trisecting a circle, so 120 degrees. The best example of this that I can give you is a fidget spinner, where you got the little central and you got the 3 legs off of it. It spins around. I don't know if these are spinning per se, not in that direction, but it helps us remember the shape at least. Okay, moving next door to group 14. Okay, steric number is going to be 4. This is carbon. Carbon always has a steric number of 4. It's really hard not to. Carbon monoxide is the only time carbon won't have a steric number 4. It'll be 3. Okay, so we've got 4 bonds, no lone pairs. We've alluded to this before. It is a tetrahedral shape, and the bond angle of a tetrahedron is 109.5 degrees. They've become a little fluffy about that 0.5 degrees. Let's be exact about it here. It's 109.5. Okay. From carbon, move next door to nitrogen, steric number 5. Okay. Or not. If it's going to bond the way we just did that phosphorus pentachloride, steric number 5. This is bonding 3 bonds and 1 lone pair. Steric number 4. Okay. Trigonal pyramidal. And because of the lone pair, that 109.5 just got bent even closer together and is now 107 even. So you're seeing a progression now to group 16. Okay. 2 bonds, 2 lone pair. Steric number 4. This is going to be considered bent. Another word for bent is angular. Depends on the book. Both terms are fine. Now, because there are 2 lone pairs, bends it even further. And now the progression we see is 109, 5, 107, 104, 5. Okay. I always remembered the 107, and then I just knew to go up 2.5 and down 2.5. That's how I get there. That's what a lone pair will do for you, is 2.5 degrees basically. So that's my group 16s. When they're bonding, 2 bonds and 2 lone pairs. Does that mean that if oxygen doesn't do that, for some reason, if oxygen bonds with 1 bond and 3 lone pairs, now we've got a little bit different shape. Okay, the shape is always based off of the bonds and lone pairs. So if oxygen bonds with 1 and 3, it's going to look a lot more like chlorine would, or fluorine, or whatever halogen you want. Okay, now my 2 exceptions. Steric number 5, phosphorus pentachloride. This is 5 bonds, no loners, called Trigonal Bipyramidal. And this one has 2 bond angles. It has an angle from the North Pole or the South Pole to the equator. And then it has bond angles around the equator. And those are going to be 120. North Pole, South Pole to the equator is 90. Bond angles around the equator, 120. Okay. And then group 16. Okay. Steric number 5. I told you we were going to get into some exceptions. Sulfur Tetrachloride. Sulfur has 2 6 valence electrons. It bonds 4, leaves 1 pair. 4 bonds, 1 lone pair. This is called a seesaw. Okay, and if we were to draw this out, what it looks like is there's nothing on top. Here's the leg, there's the leg, and here are the 2 things that are teeter-tottering. We'll build the model in class. You'll see a seesaw. It really does work. Okay, but that's a group 16, kind of a goofy seesaw shape. Okay, there's another one called a T shape. This is still steric number 5, but now instead of 4 and 1, it's 3 and 2. 3 bonds, 2 lone pairs. Okay, and your halogens do this. Not fluorine, obviously, but your group 3 and below halogens can do this, where you've got 3 bromines, lone pair, lone pair. Where's the bond angle? Right there, right there. It's 90 degrees. I know it looks like we've got 180 here, and we don't. It's just the way we have to draw it on paper because it's 2-dimensional. It looks like it is. but it's not. It's still 90 degrees. So that's called a T shape, bond angle 90 degrees. Okay. Then we have another steric 5, flip-flop it. Now we're going to 2 bonds. If you notice, we've gone 4 bonds, 3 bonds, 2 bonds, and it's 1 lone pair, 2 lone pair, 3 lone pair. This is xenon can pull this one off. Iodine can also pull this off with an I3 -1 ion. It can pull this off. This is really unique because this is the only time where you're going to see lone pairs on the central atom and the whole molecule is nonpolar. Why? Because the electrons are evenly distributed. So there's nothing, there's no positive or negative side to it. This is going to be linear. See, the lone pairs are here on the axes, but they don't take up any space. They create an electron cloud, but they really don't take up any space. So 2 bond, 3 loner, linear, and 180 degrees. Okay. More exceptions. Here's what happens is 3s2, 3p3. So we end up with 5 valence. And that's why these exceptions can occur. Okay. So all valences, 10 electrons. Same thing happens in your 16. We're going to steric number 6, 6 and 0. There's your octahedral drawn much better. Bond angles 90 degrees. You just memorize these. There's no rhyme. There's geometrical rhyme and reason, but you just memorize these. I've got a couple more. We're almost there. Still in steric number 6, because steric number 6 is as high as we go. 5 bonds, 1 lone pair. Think about this. You have 1 going up to the top and then 4 legs. A lone pair on the bottom, which is flat. It doesn't take up any space. This is called a square pyramid, a 4-sided pyramid. It's 90 degrees apart as well. Okay. And then our last Lewis structure and Vsepr shape is steric number 6, 4, and 2. And I lied. I'm sorry. This is another one where you have lone pairs on the central and the whole thing is nonpolar because they're evenly distributed. This is, I guess I've never seen one, but maybe a 4-legged fidget spinner because it's planar. It's going to be a flat molecule and it's just going to be 90 degree, 90 degree, 90 degree, 90 degree, central atom, lone pair, lone pair. Everybody's 90 degrees apart. So it's making a square. It's going to be flat. This chart is just something we've got to internalize. We've got to learn to work with. Look for the norm before we look for the exceptions, but the exceptions are there and the board uses them. I use them. Square planar, not that much. Square pyramid, not that much. But for some reason, the steric number 5s, the linear, the T shape, and the seesaw, those start to become more and more common in more complex molecules. So in a nutshell, that's sigma bonds, pi bonds, some Lewis structures, some exceptions to the octet, and all of our Vsepr shapes. That's a lot in 20-some minutes, but I'm Smath, and I hope this video helped you. Thanks for watching.